Hey everyone! You might have seen pictures of atoms looking like miniature solar systems, with electrons zipping around the nucleus just like planets orbit the sun. But is that really how atoms work? Spoiler alert, it's not. Today, we're going to dive into why this popular analogy is misleading and what atoms are really like. We aim to clear up some of the most persistent misconceptions in science education. And today, we're starting with atoms and why they're not like tiny solar systems. Let's take a quick trip back in time to the early 20th century. Scientists like Ernest Rutherford and Niels Bohr were scratching their heads, trying to figure out what these tiny building blocks of everything actually looked like. Rutherford did this famous gold foil experiment and discovered that atoms have a small, dense center, the nucleus, with electrons hanging around it. This kind of looked like planets around a sun. Then, Bohr took this idea a bit further and said that electrons could only hang out in specific paths, each with a set amount of energy. This was a big deal because it explained why atoms give off light in specific colors. When an electron jumps from a higher energy path to a lower one, it spits out light, and the color of that light depends on the energy difference. Pretty cool, right? But the Bohr model had its limits. It worked well for simple hydrogen atoms but struggled with more complex ones. At first glance, the solar system idea is pretty appealing. You've got a heavy thing in the middle, the sun or the nucleus, and smaller things, planets or electrons, moving around it. For example, oxygen has 8 electrons, just like our solar system has 8 planets. It's a neat little comparison, and that's probably why it stuck around in our minds and in textbooks. But here's where things get interesting. While this picture is easy to imagine, it doesn't quite hold up when you look at the actual science, the physics of it all. Let's break down why atoms aren't really these mini solar systems. First off, the forces at play are totally different. In our solar system, it's gravity that keeps the planets in their orbits around the sun. But in atoms, it's the electromagnetic force that's doing the heavy lifting. The positively charged nucleus has a strong pull on the negatively charged electrons. Gravity? Well, it's so incredibly weak at the atomic level that it basically doesn't even factor in. Next up, we've got different sets of rules. Planets follow what we call classical mechanics. That means if you know where a planet is and how fast it's going, you can pretty much figure out its entire path. Electrons, on the other hand, play by the rules of quantum mechanics. They don't have these definite paths. Instead, they exist in a sort of blurry state of probability, described by something called a wave function. It's a bit mind-bending, I know. And get this, if atoms were actually like tiny solar systems, they wouldn't even exist. According to classical physics, those electrons would constantly be losing energy and would spiral into the nucleus in less than a blink of an eye, causing the atom to collapse. But atoms are stable, which tells us that something fundamentally different is going on at the quantum level. Think about it this way, if electrons were just orbiting like planets, they'd be constantly changing direction, which means they'd be accelerating. And according to the rules of electromagnetism, accelerating charged particles give off energy. So, those electrons would lose energy and, you guessed it, crash into the nucleus super fast. The fact that atoms stick around shows us that electrons aren't just doing simple orbits. So, if they're not orbiting, what are electrons actually doing? Well, in the world of modern quantum mechanics, electrons hang out in regions called orbitals. Think of these as three-dimensional spaces where there's a high probability of finding an electron. For example, the simplest type of orbital, called an s orbital, is a sphere around the nucleus. The electron could be anywhere within that sphere, but we can't pinpoint exactly where it is at any given moment. This fuzziness is due to something called the Heisenberg Uncertainty Principle, which basically says we can't know both an electron's exact position and its momentum at the same time. It's like trying to catch a fly in a dark room. You know it's in there, but you can't say exactly where it is right now and where it's going next with total certainty. You might sometimes hear the analogy of a fast spinning fan. When the blades spin super fast, they look like a blurred circle, and you can't really say exactly where each blade is at any instant. This gives you a rough idea of the electron cloud, where the electrons are kind of smeared out around the nucleus. Now, it's important to remember that even the fan analogy isn't perfect. The fan blades do have definite positions at any given time, even if we can't see them clearly. That's classical physics. But for electrons, their positions are fundamentally uncertain due to quantum mechanics. They don't have neat little trajectories like the fan blades. So, the fan is just a simple way to visualize the idea of a probability cloud, but it doesn't capture the full weirdness of quantum mechanics. So, to put it simply, electrons don't orbit the nucleus like planets. Instead, they exist in these probability clouds called orbitals. It's almost like they can be in multiple places at once until we actually try to look for them. These orbitals come in all sorts of shapes and sizes, depending on the electron's energy level. Some are spherical, like the s orbital, while others look like dumbbells or even clover leaves. And unlike planets that mostly orbit in the same flat plane, orbitals can be oriented in all sorts of different directions in three-dimensional space. Another big difference is that electrons can only have specific amounts of energy. They can only exist at certain energy levels, not just any distance from the nucleus. This is why atoms produce those distinct spectral lines when they emit or absorb light. It's because electrons are jumping between these fixed energy levels. Think of it like climbing a staircase. You can only stand on specific steps, not in between. Planets, on the other hand, can orbit the Sun at pretty much any distance, as long as they have the right speed. There are no energy levels restricting them. Let's also talk about size for a second. Atoms are mostly empty space. If you blew up an atom so that its nucleus was the size of a pea, the entire atom would be about the size of a football stadium. That's a crazy amount of empty space. In our solar system, the Sun is obviously huge compared to the planets, but the distances aren't quite as extreme proportionally. For example, the solar system's diameter, to Neptune's orbit, is about 6,500 times the Sun's diameter, a considerable emptiness. Yet, an atom's diameter is roughly 100,000 times its nucleus. Talk about varying degrees of profound emptiness. So, why do we still see that solar system analogy everywhere? Well, despite its inaccuracies, it's a really simple way to introduce the basic idea of atomic structure. It helps you picture the nucleus in the middle and the electrons around it before we dive into the much more complex world of quantum mechanics. But to truly understand what atoms are like, we need to move beyond that simple picture and embrace their quantum nature. Alright, let's do a quick recap. Atoms aren't like tiny solar systems because they're held together by electromagnetic forces, not gravity. Electrons exist in probability clouds, orbitals, not fixed orbits. Electrons can only have specific, discrete energy levels, unlike the continuous orbits of the weirdness of quantum mechanics, like the uncertainty principle and wave-particle duality, just doesn't apply to solar systems. So, while that solar system analogy is a helpful starting point, it's super important to realize that the real world of atoms is much more bizarre and fascinating. Now that you know atoms aren't like tiny solar systems, what other science concepts have you questioned? Share your thoughts and any other misconceptions you've encountered in the comments below. Let's learn and explore together. And remember, question everything and learn more. See you in the next video.